freeze it.
Is this your background? Or?
No, no.
I think that's this background. So,
which one is plugged in? Do we have
That's fine.
But it's not the background.
It's not my background at all.
maybe it's not this one?
It detects it.
Good. Oh, that's funny.
Why is it coming up that? I don't have that background at all.
Very strange.
I
also not
plug this
local
out.
difference.
Yeah.
I don't want to turn on mirroring.
Can you restart?
And I can do a full reboot, but
Yeah.
What is that?
that's painful. God, it's hard.
Restart.
Yeah, it's just hard to believe that that's should be necessary.
Okay, it's
it's
definitely
already
connected.
connected and
Yeah,
stuff, right?
definitely connected. So then I don't understand.
Okay, well, this is trying to get itself going. I might as well take this opportunity to, along with everyone else, wish David happy birthday. We are a few months shy of the 40th anniversary of when I met David, and we started talking a lot. At that time, he was a lot younger than he was today, as was I. Nevertheless, he seemed like this towering, mature figure compared to me, decade and a half between us. And certainly over the next few years, I can't really describe how much I benefited from my interactions with David. I really appreciated his generosity with his time. He did intimidate an awful lot of students. I was reassured by the students who were slightly ahead of me that in the time he'd been at Princeton, he'd already mellowed out a lot. And so it was almost all to the good, except for one thing, which was the same thing that Igor mentioned a few days, except this was pre the cigar era. This was the cigarette era. But what could one do? Everybody interesting going through Princeton spent a huge fraction of their time in David's office. If you wanted to hear about interesting stuff that was going on, you tried to act like a little fly on the wall, and that's what I did. And we're still, whoops, that's not what I wanted. We're still not connected. What is that?
That's funny.
What do you want to do?
USB. Maybe you can just connect to this machine.
I don't have a stick with me. I can certainly.
Do you have a USB? Do you have a USB? Maybe you can copy to here.
There's no choice.
Oh, this is your background.
Yeah. It appears somewhere on the computer.
Before.
Anyway. You never know what your backgrounds are. Okay, yeah, now it looks good.
No,
All right.
that's right.
Okay.
That's fine?
That's
Yeah.
doing much better.
Yeah. Okay, very good.
good question.
What? Something
You didn't know
we
he's
don't know
back.
how to.
No, just to mirror the screen. Okay, so let's start. So second speaker is Laurence Yaffe from University of Washington. Lessons from Numerical Holography. Please go ahead.
Thank you. So always interesting to be following Shiraz. May not be quite as high energy. Don't go to sleep. And don't believe the last few things he told you.
You mean I wasn't terrified by David?
Okay. So in this audience, I don't need to say anything about gauge string duality, how it leads to a useful mapping between quantum field theories, which you may choose to be interested in, and in a large N, large coupling limit, classical gravity. I don't need to say we've learned a huge amount from studies of ADS-CFT duality. I just want to remind people that in the context of thermal physics of non-abelian gauge theories, almost all of that work, for completely understandable reasons, has been studying equilibrium properties or near equilibrium properties. You find equilibrium solutions, then you shake them a little bit, and all kinds of interesting stuff has come from that. A better understanding of thermodynamics, a celebrated calculation of entropy to viscosity densities, higher order transport coefficients, all kinds of probe dynamics, wakes of projectiles moving through a medium, holographic models of a whole variety of interesting systems. What I want to focus on, though, is to say that once you've had great fun in that playground, it's natural to ask, well, can this mapping actually give us useful information for what you might call real hardcore dynamics? Take a system and don't make just some infinitesimal little perturbation on it. Give it a big whack, push it far from equilibrium, and just honestly say what happens. And the great thing about the duality is it says we have an exact mapping between theories. We can use it to study any states of interest we want. So roll up your sleeves and get to work. The challenge, of course, is what can you really calculate? So I think it was back in 2008, I was at a program at the KITP that had some of these words about non-equilibrium dynamics in it probably. And in interactions with some of the other people there, I basically decided it was time to get serious. So channeling Richard Feynman, the message was to shut up and calculate. So take advantage of the fact that the duality maps quantum field theory dynamics, where I remind you, in theories that are not arbitrarily weakly coupled, we have no controllable methods whatsoever to do real-time dynamics. But in this very special domain, boom, you apply the duality, it says it maps it to gravitational dynamics, and the whole point is in the large N limit, it's classical gravitational dynamics. So it maps non-trivial initial state problems in a quantum field theory into, well, non-trivial gravitational initial value problems, but they're classical, and that just means solving some set of ugly equations. All right? Far from equilibrium dynamics, you've got to pick what particular state or question you're interested in. An obvious statement is interesting things to look at will be simplified versions of things you should think of as actually experimentally relevant. That typically means either some version of scattering experiments or some version where you start the system in some state that you understand, equilibrium, but then you turn on some time-dependent external field. You disturb it. All right, and this has led to a lot of stuff, much of it motivated by efforts to understand better heavy ion collisions, a classic example of a scattering experiment, but where you're producing some quark-gluon plasma, which is in a strongly coupled regime, and we don't have reliable calculational tools. Okay, so can you actually do it? Over the last, what's it been, 8 years, you can infer that the reason I'm talking about it today is that we know how to do things a whole lot better than we did 8 years ago? And so the answer is basically yes. I will spare you the hour or an hour and a half long discussion of details and technical aspects, but I just want to flash up here sort of a little timeline of some of the things that have been done. And I made a serious, overlooked a serious comment at the very beginning, which is to emphasize everything I'm talking about today, almost everything I'm talking about today, represents work done in collaboration with Paul Chesler, who back in 2008 was my graduate student. Okay, but we're trying to solve 5-dimensional Einstein's equations because we're interested in dynamics of 4-dimensional maximally supersymmetric Yang-Mills theory. Simplest problems are ones which have enough symmetry, so you don't really have to solve 5-dimensional partial differential equations. First thing we looked at I call homogeneous isotropization. Think of it as saying you have some box of plasma and you simply completely uniform, homogeneous in space. And if you want, think of it as a gravitational wave passing through, but all that matters is you're simply shearing this box. You're stretching it in some directions, you're compressing it, this is producing an anisotropic plasma, and then you let it go and you say what happens. So that's one easy way of probing thermalization dynamics. And if you shear it a lot, you can really drive it very far from equilibrium. You can make it arbitrarily anisotropic. And that has enough symmetry. It reduces 5-dimensional partial differential equations to just 1 + 1 dimensions, which is a lot easier. And we did it. And we did a version of boost invariant expansion, which I won't say anything more about today. A natural next step, if you've succeeded here, is to then say, well, think about heavy ion collisions. What are these? These are collisions of large but highly Lorentz contracted nuclei. Think of them as very thin pancakes. They come together and slap. Think about a limit where they're really infinitely large pancakes. So in other words, imagine that everything is infinite and uniform in transverse directions. That looks then like collisions of infinite planar shockwaves, surfaces on which you have some excess of energy density, and that's something you can mimic perfectly in n = 4 super Yang-Mills or its dual gravity description. So a few years later, we looked at that. I'll spend a few minutes later talking about turbulence, which is not my own work, but is Paul's work with Hong Lu and Alan Adams, and it's a really beautiful example of seeing fun physics coming out of the gravitational description. And more recently, for the first time, we succeeded in doing something which actually does mimic a heavy ion collision, that is to say, finite size nuclei in quotes. That is, if you want, call them shock waves, which are finite in both the transverse extent and in a longitudinal direction, really do look like Lorentz contracted nuclei, really do bang them together, whatever impact parameter you want. We really did non-zero impact parameter and see what comes out. And at the end, if I have time, I'll say a little bit about a project where I hope to show you some results, and I don't have any. It's work in progress, but I'd still like to mention it as far as interesting ongoing questions. Okay, I titled my talk Lessons from Numerical Holography, so I take that as my goal to try and talk about various lessons that I think we've learned along the way. Some of those lessons are computational, and I'll just summarize them really quickly. I want to spend more time on sort of physical messages. On the computational side, there's one big message here. There's something called characteristic formulations of theories like gravity. That's a buzzword for saying that instead of thinking it as an initial value problem where you use Cauchy surfaces that are spaced like slices, instead you use a null slicing. It's actually a lot more than that. What you're really doing is directly tying the coordinates that you're using to describe this non-trivial space-time to a particular congruence of null geodesics. And in all the problems I'm going to talk about, that's a really physical choice of a null congruence. You have space-times that are asymptotically ADS. You should think of the boundary as being ordinary Minkowski space. You should imagine you have some family of observers on that boundary, and this is literally null geodesics that emanate from the boundary, from every one of your boundary observers, you know, shining a flashlight and pointing it into the bulk. So you get rid of most of the diffeomorphism freedom by tying your coordinates directly to those geodesics, and some amazing things happen. First of all, you don't have problems with future horizons. These are coordinates nicely adapted to gravitational infall and collapse problems. Technically, this horrible set of coupled nonlinear partial differential equations, if you look at them the right way, they fall apart into a nested series of linear radial ordinary differential equations. And you know how to solve linear ordinary differential equations. Even if you can't do it analytically, that's not a tough problem to do on a computer. Now, of course, you're doing it over and over again, basically for every one of those boundary observers. But still, it's just linear equations. Wonderful. All right, this was new to me 8 years ago. I was not a professional relativist. Sometimes it's good to be an amateur. The professional types knew about characteristic formulations, and they essentially never used them. They said this is useless. Because, although this is a wonderful formulation, since you're tying your coordinates directly to some particular set of geodesics, if those geodesics intersect, that is to say, if you have caustics in your set of geodesics, that is directly producing a coordinate singularity. Bad news. And if you are interested in something like colliding black holes, you imagine you've got a couple black holes spiraling around each other. You imagine you have some geodesics that are coming in and being bent by the gravity of those black holes. It's easy to imagine cases where you'll have geodesics forming, and that'll screw up this method unless you now switch from one, use patches and different geodesics and other patches. Terribly complicated. However, I'm not interested, well, for today, I'm not talking about problems that involve asymptotically flat spacetimes and that sort of colliding black hole physics. I want to focus on problems which are asymptotically ADS because I'm interested in the dual field theory aspects of it. And major message is that in many respects, doing asymptotically ADS general relativity is easier than asymptotically flat spacetime. A big part of that, well, is tied to the class of problems I'm interested in. I'm going to be looking at problems where you do have some form of black brane. It may be very dynamical, it may be wiggling around a lot, but it will eventually settle down. Black branes physically represent the fact that you have dissipative physics. Asymptotically ADS, loosely speaking, means stuff falls down. So that's not only true for physical stuff, it's basically true for numerical garbage, right? Any discretization scheme produces some sort of short wavelength numerical error. You worry about how that's going to propagate to the future. In this setup, a big part of the message is a lot of the numerical difficulties, what do? They fall through the horizon and go away. All right? Just as Shiraz said, I'm only interested in calculating what's going on outside the horizon. Good. So the bottom line is this really works. Well, I can't say it works for all problems. It works for a very wide class of problems, and physically it just depends on what I said here. It works as long as the characteristic time scale associated with the dissipation, which is sort of this gravitational infall time, it works if that's the shortest relevant time scale in the problem. You can obviously engineer cases where that's not the case. But as your doctor says, if it hurts, don't do it. There's a lot of interesting physics where that's not the issue.
So the simplest example of this would just be fluid dynamics. Right?
Sure.
This is true in fluid dynamics. It's interesting that not just for numerical, but also for analytical purposes, these same coordinates will be true.
Absolutely, absolutely. And I was directly influenced by some of that early work.
Is this the same as so-called holographic gauge?
let's talk about that later, because I don't honestly know what you mean by holographic gauge. But I'm happy to talk about that later. I'm going to suppress all those details. This is what you could call a generalization of infalling Eddington-Finkelstein. It's very closely related to what's been used in fluid gravity, but that's a detail. Second message, real quickly. Smart people, as you heard 5 minutes ago, say, oh, it's really hard to do numerical problems like this. You have the sense that it has to be. Something which is not new, but I think is not as widely appreciated in our community as it ought to be, is that there are methods for doing numerical differential equations which vastly outperform sort of traditional short-range discretization methods. This goes under the buzzword of spectral methods. It's really just using what we know about properties of Fourier series and analyticity. The short answer, though, is when you have sort of suitable problems, you're going to discretize, you're going to have some number of grid points, and with spectral methods, you can get exponentially rapid convergence as you increase the number of grid points, and that is just hugely advantageous. More technically, every equation, you look at quasi-normal mode equations, everything in asymptotically anti-de Sitter space, that boundary ends up being a regular singular point. And you have to have numerical techniques that easily cope with regular singular points. The nice thing with spectral methods is you don't have to sort of carve a little region around it and do it separately. You can just directly apply spectral methods when you have regular singular points, as long as the specific solution you're interested in is well behaved at that singular point. And I'd be happy to talk about that more. Bottom line, I'm going to show you some results, all of which just came from desktop scale computing. This is not supercomputing. I'm not a supercomputing type of person. And given whatever time I have, I'd like to now show you a sequence of results of increasing complexity and talk just a little bit about what's been learned. And so I mentioned homogeneous isotropization is sort of the oldest problem. I'll say a little bit about actually some much more recent work looking at the sensitivity of that equilibration dynamics when you actually change the makeup of the plasma, where you turn on a chemical potential or something. This is interesting for a number of reasons, one of which is if you're doing all of this because you're interested in real QCD and the physics of quark gluon plasma, here I'm talking about some toy model theory, which is a supersymmetric plasma. It's the wrong theory. Very basic question is, how much difference does that make? That's a hard question to answer because we don't have a good dual of QCD. But one at least small step in that direction is just say, do what you can. Change the precise makeup of your supersymmetric plasma by turning on some flavor chemical potential and just see how much difference does it make. Okay, well, that pretty much says what I already did. Real heavy ion collisions, there is some baryon chemical potential. A reasonable question is, how much difference does it make? The gravity side, it means we're looking at Reisner-Nordstrom black brains. As you change that chemical potential, I want to point out that as you go, say, from 0 charge density to there's an extremal value, I'm going to show results up to 80% of that extremal value, and quasi-normal mode frequencies change by about 10%. So that's not a huge amount, but it's a significant amount. It's easy to see. Okay, I'm going to take the system. I'm just going to start with some initial state where I put some anisotropy in. Happens to be a Gaussian bump in the bulk. And we're going to calculate in the field theory what you see in the stress tensor. Okay, so that perturbation as a function of time running this way, this is the anisotropy difference in two eigenvalues of the stress tensor. It actually takes time for that influence to propagate out to the boundary. Then you see some big peak. Value of 100 here. This is normalized to the pressure. That's a giant anisotropy, right? That's hugely far from equilibrium. All right, but big peak, wiggles, ring down. Hey, it's almost like what we just saw from LIGO. This is not the lowest quasi-normal mode. right? That describes what's happening asymptotically far out when the perturbation is asymptotically small. All right, I'm going to show you results as I change the charge density, 0, 20, 40, 60, 80% of extremality.
I missed what your perturbation was.
Perturbation was just fixed. So I'm just, in this case, I'm not doing something which is really a physical Gedanken experiment. I'm literally just starting with initial data on some initial null slice. That initial data looks just like anti-de Sitter space, except by hand, I'm putting in a Gaussian perturbation that is shearing 2 dimensions relative to the third. And I can show you the details. OK, so I want to show you the results for these other 4 cases. And here are the results. They're right there. Curves are all on top of each other. You cannot see the difference. Remember, I told you quasi-normal mode frequencies change by 10%. That's remarkable. I could say a little bit more about why I think that came out, but I don't have a really great story. I think that's remarkable. Now, you can change exactly where you put this initial Gaussian. You can make somewhat more sense. It's really, really hard to get initial choices which produce any big effect at all. That's pretty remarkable. Real heavy ion collisions, you actually have, of course, electrically charged stuff. There's been a lot of discussion about electromagnetic effects. That's a hard question. An easy question is just turn on a constant magnetic field. Let me show you exactly the same thing with a background magnetic field. There are some technical aspects of this that are kind of interesting. It actually means there's a scale anomaly. It has complications on the holographic side I'll say nothing about. Here are the results. Same sort of setup. Response is a function of time. Big, huge anisotropic pulse. Ring down. Sure, there's difference due to the magnetic field. This is going from 0 magnetic field to a magnetic field compared to the relevant scale. That is a dimensionless number b over t squared of 30. Right? That's going from a very low field to a very high field. Practically no change. Isn't that weird? OK, lessons. I already said a few of it. Really does show you that the characteristic time scale is a gravitational infall time. Remarkably little sensitivity to exactly what the constituents of the plasma are or to some background magnetic field. I didn't show you tests of linearity, which are also interesting to do. Big, complicated, nonlinear Einstein's equations as measured by this boundary observable. Turns out it's surprisingly close to linear dynamics. OK, I just want to keep forging ahead. Let's look at a more complicated problem, that of colliding planar shockwaves. Something which was first done, I don't know, 6 years ago or something. Now, when we first did it, well, so let me first specify. So colliding planar shockwaves, there are exact trivial solutions which describe a single planar shockwave moving along at the speed of light. And it can have whatever longitudinal profile of energy density that you want. You can make it a delta function. You can make it a smeared out delta function. Numerically, you know, the sharper it is, the harder things get. So in our initial work, the width of those planar shocks compared to the relevant scale, which is what's set by their energy density, they were not incredibly narrow. More recently, actually 2 different groups, including one with Paul, one without, have looked at much narrower results. And so it's interesting to see what, if anything, has changed.
The shockwaves are moving in the radial direction?
No. These are, so in the field theory, these are infinite planar shockwaves moving in, call it the z direction at the speed of light.
How do they extend up to the radial direction of ABS?
So in the dual description, there is a particular, ansatz for the metric, which tells you what is the right radial dependence given some choice of the boundary data. And I can write it down for you. For these, you have metric functions which grow like a power law as you move into the bulk.
Particular decays are really normalized.
Oh, absolutely. Because that's what matches the physical question I want to study. OK, so this is plotting energy density as a function of time coming out this way, longitudinal direction that way. The back end of this, you see the peaks of energy density coming in. They hit, boom, peak of the energy density. What comes out is some sort of smeared out version where you're seeing the forward light cone, if you will. There is excesses of energy density very close to the two ends of that outgoing light cone, but there's energy density spread all the way in between. This is, of course, what happens in real heavy ion collisions. All right, that's a relatively wider shocks. Here's a more recent picture of much, much narrower shocks. I would say nothing dramatic changes. There's one group which tries to put a different story around it and say, no, it's clear. I don't see any big difference. It's sharper. In particular, you have energy density localized very close to the light cone. It is obviously decaying away. Right? There's no surviving stable remnants on the outgoing light cone. There's energy distributed in between. You can look at this in detail. An interesting thing is to actually look at the rapidity dependence of the energy that's in the interior of that outgoing light cone. It is stunningly close to having a universal Gaussian form, which doesn't have a good explanation. 5 minutes, wow. Okay, that was planar shocks. Real nuclei have finite extent. There's both transverse and longitudinal dynamics. Sort of a motivating goal from the earliest days was, well, maybe eventually we could get to the point where we really do things which are truly mimicking heavy ion collisions. That means full, honest-to-God, 5D Einstein's equations. No dimensionality reducing symmetry restrictions. Wow. Well, we managed to do that a little over a year ago. Let me show you a movie. Again, plot of energy density. Here's profiles of my initial nuclei. These are not the most realistic profiles of honest nuclei. These are whatever else, Gaussians, because Gaussians are easiest. They come together. They go boom. Stuff flies out. And all that energy density is left in between. It may not seem like that evolved for a very long time, but a key question is simply, have you evolved long enough that you could switch from a description that's full GR to an effective description, which is fluid dynamics, right? So an obvious question is to say, how accurate is hydrodynamics in describing what comes out? Oops, I forgot. So this is just snapshots of what I just showed you. Energy density or energy flux. This is what I wanted to say. A natural thing is to take your calculated stress tensor that came from doing full GR and compare it to an approximation you would get by using hydrodynamic constitutive equations. Form a figure of merit where, again, you normalize it to the average pressure. This is showing that figure of merit. So if it is so the scale here is 0 to, well, 1 is up there. Oh, sorry, that is rapidity. So this first row is 0 impact parameter, and the second row is, sorry, I didn't say that right. Everything is non-zero impact parameter. The first row is looking at what comes out at 0 rapidity, and the second row is looking at what comes out on a boosted axis. All right. What do you see here? You see a little blue blob. That's your droplet of fluid, right? That's where the hydrodynamic residual is small. That's where it's saying it's well described by hydrodynamics. So this is a little formation of something that you'd think of as a blob of hot plasma that is behaving hydrodynamically, and it does what it has to do. It expands. All right? You look at non-zero rapidity. It first sort of forms off center. It expands. And an interesting thing is how quickly it is well described by hydrodynamics. I'll say that in more physical terms a moment later. The most direct test, I would argue, is what I already said. Simply, is it well described by hydrodynamics? Where when I say that, you're using the equilibrium relation between energy and pressure in evaluating the constitutive relations. 2 minutes. Ah, terrible.
What if you want to see the hydrogenization process? Eventually it's not
Absolutely, absolutely. So I'm studying some caricature of real QCD here, where I'm modeling it as a conformal theory. All of the real physics of hadronization has been thrown away or pushed to later times I'm just not going to. But the claim is you look at real lattice data on hot QCD, and in an experimentally relevant temperature range from the highest where it makes sense to talk about temperature, 4 or 5 times Tc, down to maybe 1.5 times Tc, results are surprisingly close to what you'd expect for a conformal fluid. Now, it's obviously then breaks down when you get closer to Tc and below.
By playing with the parameters, could you see any resonance effects?
First of all, there hasn't been that much playing with parameters, because even though my message is things are a lot easier than you might have guessed, 2-week run times, you're not really motivated to do a lot of parameter exploring, and so no. I think I will skip over saying anything about turbulence, even though that's a really fun story. I was going to show you some results for both normal fluid turbulence in 2D, where the message is not teaching you anything about fluids, it's just that you can actually reach sufficiently large Reynolds numbers to see turbulent behavior in something that you can do computationally with desktop scale computing resources. So that's pretty impressive. I was going to say a little bit about 2D superfluid turbulence, where one of the nicest things that comes from this holographic treatment is answers to questions that were actually unclear in the condensed matter literature, whether for 2D superfluids you have a direct cascade of energy or an indirect cascade of energy. It's a beautiful movie, too. Correct. So it's a direct cascade in 2D, unlike the case of normal fluids. All right, beautiful work, which I'm not going to do justice to. Whatever remaining minutes I have, 0. 0 is a terrible number. So I wanted to say something about a problem where I can't show you results, but it's what Paul and I and Alex Buchel are currently working on, and I hope we'll have results later this year. And it's a question which I find sort of, well, obviously intriguing and puzzling because it's not some terribly complicated setup. So ordinary confinement dynamics. Take your same n equals 4 theory, but instead of viewing it on infinite Minkowski space, put it on R3 cross, put it on S3 cross R1. In other words, put it in a spherical box, in which case an old story is that there is a confinement transition, there's a low temperature confined phase where thermodynamic quantities are of order n to the 0, there's a high temperature deconfined phase, there's a first order confinement deconfinement phase transition. That field theory description is claimed to map beautifully to a gravitational description where you have one gravitational solution which is just periodically identified pure ADS, that's called thermal ADS, and then you have black holes in global ADS. I happen to write a metric here. And as I certainly know many of you are aware of, you actually look at the thermodynamics of small black holes in global ADS, and you can freely change the radius of those black holes, or equivalently their energy. And the free energy has a plot that looks like this. Thermal ADS has a free energy of 0. Equilibrium is minimizing free energy. So this says the black hole minimizes free energy only when rho is larger than something that's 1 in the units I'm using. And so there's a branch of black hole solutions up here which are not thermodynamic equilibrium states, so-called small black holes. Fine. Question, what do they mean? Well, it's a first order phase transition. Any first order phase transition you should be able to supercool. So obvious interpretation is that these small black holes are describing supercooled plasma. Now normally you supercool through a first order phase transition, there's some limit of metastability. At some point you'll reach that limit, you'll have what's called spinodal decomposition, and the system falls apart and discovers that there's another phase. Well, that almost matches just what's known. As you decrease the radius, at some point there is a dynamical instability that's a variant of the Gregory-Laflamme instability. This is true when you pay attention to the fact that the correct dual description is not just 5D gravity, it's really cross S5. And this instability is associated with deformations of that S5. So there's a critical value below which there's an instability. Question, where does that instability go? This is not understood, to the best of my knowledge.
Was it just a 10D black hole? Small 10D black hole?
This is speculated to be true. So you imagine that what you're seeing is localization of that black hole instead of having it smeared over the S5, that it eventually end up being localized on the S5. There's been efforts to find such a solution. The only solutions that have been found have lower entropy or higher free energy, so they're not the right ones. And in any case, there are still questions. So that's what I tried to say here. So we're just literally trying to follow that instability by doing honest-to-God time-dependent dynamics with what is now 10D GR plus a self-dual 5 form. We think we can do that. I could say more about complications. What I want to point out in terms of questions really focuses on this. I've got some thermodynamic system. I can think about what's going on from a canonical perspective. I can think about what's going on from a microcanonical perspective. Those two pictures had better be consistent. Well, we have these small black holes. They become dynamically unstable. They do something. Maybe they turn into something where the black hole is localized on the S5. Well, that's telling you then in the dual field theory there's an equilibrium state you weren't aware of that has smaller energy density than what you thought was the minimal energy density when your whole sphere was filled up with hot plasma. What is it? Also, this came from deforming the S5. This means you're talking about states which are no longer invariant under the full R symmetry. In the canonical description, there's no hint of any spontaneous breaking of R symmetry. And yet here we are talking about solutions which are not invariant. Now, normally, in first-order phase transitions, you have coexisting states right at TC. We have descriptions of what I would call the two extremal states. Normal first-order phase transitions, you have a whole manifold of coexisting states that interpolate between. Where are they? We have no dual description of such states. In an abstract sense, you can simply superpose the density matrices. Now, in any normal system, that state, which would violate cluster decomposition, is closely related to a more physical one where you have some sort of phase separation, and you're back to a state which does cluster. That's what we don't know how to, that's what these small black holes might have something to do with, and I'm just going to leave it here. It's a question mark. I don't know how to interpret it. All of this is part of what I think numerical holography has been a sort of fun tool for. It's been fun to get involved with it. And as David said in his talk, however much progress you make always just leads you to more interesting open questions. Thank you.
To another building for Anisotropy's talk, so I want to just cut off with very short question. Okay, sure.
Sorry, just as we discussed before, this phase with coexisting phases. At least if you look at the weakly coupled version of this problem, it's a matrix model. If you can find all the saddle points of the matrix model, this coexisting phase saddle point does not exist. So I just think that intuition's wrong. That you should get these.
I'm prepared to believe that. But then you still need an explanation for where does this dynamical instability lead.
Those are the small black holes.
The,
The 10 liter.
so you're saying there's a new stationary 10D black hole solution with higher entropy and lower free energy. That may well be. It hasn't been found. And it would say that there are equilibrium states of broken R symmetry, which would be an interesting new message.
Locally, it can make a fork shield, which just maps onto ADF time from the style of light. That's the expected solution.
That's what many people expect. I'm not disputing that. It hasn't been found to the best. I mean, there have been efforts. It hasn't been found with the with a free energy that actually makes it the right endpoint. And again, whatever your story is here, you have to have, I claim, a reinterpretation of it that would make sense in a canonical description. And that's really been overlooked.
Sorry, evolution in GR fixes the energy, it doesn't fix the temperature.
Yes.
The microcanonical story one has to follow. If you're talking about
Fine, fine. Now the endpoint of that microcanonical ensemble is some equilibrium state with some given energy density, which I can ascribe to some given temperature as well. It should be a state that I can put on a phase diagram labeled by temperature just as well. I'm not disagreeing with you what you said. I'm saying there's sort of part of the interpretation that's still missing, and there's not, to my knowledge, a satisfactory, consistent story.
These are all likely to be all unstable saddle points. So you don't see them as leading saddle points. Typically, small black holes just don't show up in the leading canonical description. You jump from a gas to the big bang.
I think, you know, we need to cut this off.
Yeah.
Let's
Okay.
talk about that some more. The challenge is to see that you're ending up in the other phase, you have order n squared energy.
Yeah.
It doesn't
Okay.
look like your thermal gas.
Okay, let's thank the speaker again, and just follow